about traditional inverse spectral problems. When given some spectrum of scattering data, normalizing numbers, we try to restore the potential of the problem or some coefficients, boundary conditions, but all the facts we look for are functions. In our case, we also have to give some data and define the domain of the problem. We try to restore the domain where the process occurs, and in mathematical terms, we can say that we try to restore the domain where the problem is given. In this case, we have indeed two problems to be solved. First problem is to identify the spectral data. What we have to give to restore the domain. And the second problem is using the given spectral data to identify the domain, to give some procedure, some approach, how we can find the domain. The spectral data, usually we know from the general theory, they should be measurable and they should be expressed by the spectral parameters of the considered problem. Here I give some picture about the spectral problem when in Middle Africa many years ago, different tribes had different instruments to play. But they had indeed different shapes, surface shapes, and they indeed produced different sounds. And the chief of some tribe can listen and define what tribe now plays. Indeed, the person you see, he solved the inverse problem with respect to domain, estimating some signals from instruments. He tried to define the shape of the instrument played. General mathematical formulation, again, traditional what we have. We have some operator A, given some eigenvalue problem with some boundary condition, for example, Dirichlet condition, in some fixed domain D, where lambda is eigenvalues and the U is eigenfunctions of the considered problem. General formulation for our case is almost same, but we have some very big difference that the domain D here is not fixed. And if you solve this problem, we get eigenvalues, eigenfunctions, but as the domain is not fixed, is variable, in the arguments of these quantities, we have domain. Indeed, we get some domain functionals. The functional with the domain in its argument. In such formulation, there arise different kind of problems to be studied. First, behavior of the eigenvalues and eigenfunctions with respect to D. Generally, if we consider some special cases, some simple cases, for example, eigenvalue problem for elliptic equation with first boundary condition, we know that when the domain enlarges, the eigenvalue becomes smaller and smaller. But generally, we have no some algorithm demonstrating the behavior of the eigenvalue with respect to domain. When we change domain, we have no any imagination how the eigenvalue will be changed. The second type of problems is shape optimization problems for the eigenvalues. As we said, in our case, eigenvalue is a functional of domain, and the shape optimization problem means that from some admissible set of domains, we have to choose a domain that minimizes the eigenvalue of the considered problem. This is general formulation of shape optimization problems for the eigenvalues. The third kind of problems is inverse spectral problem with respect to domain. I told about this problem a little. What is the difficulty in studying these problems? Of course, the object and the investigation you see are shapes, domains, and usually we have very big problems when instead of functions in the arguments we have some domains. And this condition, this formulation produces very various types of difficulties that we have to solve to investigate out. What is, for example, big problem? Unfortunately, this is PDF and I cannot demonstrate the motion of the domain. One of the main difficulties here is to give the good mathematical expression, the description of the domain variation. What does it mean? How mathematically express when we give some variation to the domain. Here's some history about history of investigation of these problems. Sea and Sokolovsky-Solozhev, they introduced some method to investigate variable domain problems using the vector field definition. This is, of course, is very good method and allow to solve a very large class of problems. But this technique has some defects, we can say also. Why? Because here we have problem of how to connect the set of admissible domains with a vector field. What does it mean? To give some variation to the domain by this technique, we choose some direction, and in this direction we vary our domain and get something new. But if after each variation we have to turn back and check, does the new domain belong to the set of admissible domains? This method also requires high regularity on the initial data. This method requires reducing the conditional problem to non-conditional problem, and calculation of the gradient by this method is always delicate, seldom exact, and generally very expensive. Calculating the gradient by this method, we usually get very, very big formulas that sometimes becomes useless in applications. What we have done, the idea of the new shape derivative theory introduced by us is to express the variation of the domain by its support function, by the variation of its support function. But in this case, we have to consider convex domains, because only in the case of convex domains, we can talk about support function. The main idea is replacing variation of the expressing variation of the domain by variation of the corresponding support function. By this way, we again come from working with domains, come to working with functions. This is the definition of the support function. This is known formula. Also, it is known that there is some single-valued correspondence between bounded convex domains and continuous convex positive homogeneous functions. If we have some bounded convex domains, then we have continuous convex positively homogeneous function that is called support function of this domain. The opposite statement is also true. For each good function, I'll try to be very simple. For each good function, we have a good domain for which the function is a support function. So there is one-to-one mapping between continuous convex positively homogeneous functions and the convex bounded domains. And if we have support function, how can we reconstruct the domain? There is a formula that if we take subdifferential of support function at the point 0, we get some domain. Subdifferential of the support function gives us a domain for which this function was a support function. So, having support function, we have a way to restore the domain. What kind of positive moments gives this approach? This is very good in numerical solution, because before, if you don't apply this method, after each iteration, we got some set of boundary points, and we had to check every time, does the set of boundary points form a boundary of the convex domain generally? It is a very big problem, because sometimes this obtained set of boundary points can be self-crossing and not form a boundary of the domain. Second, if we got some support function, we can take sub-differential of this function at the point 0 and get another. Also we have some good result here is, I'll talk about this. This approach allowed us to prove differentiability of the domain functional and calculate its gradient with respect to domain. Here I told about that, and the last one is doing some research in this direction. At last, we arrived to the point where we can consider even inverse spectral problem with respect to domain. Now, we consider some set of domains K, where K0 is some restriction that may be given by different ways. For example, we can define K0 by fixing the volume of the domain. In two-dimensional case, I can consider the set of domains with fixed length of boundary. In multidimensional case, maze of boundary, for example, or the K0 can be defined by the second way. The D should be between two given domains, and investigate our problem in such set of convex domains. I told about the fact that in the variable domain problems, we have functionals with domain as argument, and to work with functionals, the main tool we have to introduce is the space where we can work, because usual spaces are not suitable here, because for these spaces we have functions as elements. So one of the main our impact to this direction is the definition of the pair of convex domains space. We introduced a space of convex domains with the operations you see. And we proved that this is a good space where we can work. We introduced a scalar product in this space. As you see, the scalar product is expressed by support function of the domains. You can see here. If we have scalar product, of course, we can define the norm in this space. This is the main impact. Then we give the definition of derivative of the domain functional in the space. You see, this is the definition of the functional with domain argument. Now let's consider the concrete case problem. Let's consider Schrödinger equation, or we can say eigenvalue problem for the Schrödinger equation with the Dirichlet boundary condition. Here, these convex bounded domain and the Laplace Q is differentiable non-negative function. Here we have, this is our restriction, this is our limitation. We give some additional condition on Q, that Q must satisfy the additional condition. Now we cannot say that we solve this problem for all Q, but for the Q satisfies the additional conditions, we will offer some approach. We introduce some new definition of S functions of the considered problem. For example, we have eigenvalue problem for Schrödinger equation with Dirichlet boundary condition where the potential Q satisfies this condition. And for this problem, we introduce the definition of S functions. As you see, the S function is defined by gradient of the eigenvalue divided by eigenfunction divided by eigenvalue on the boundary of the domain. The S function is defined on the boundary of the domain. As we see, this is measurable and this function is expressed by spectral parameters. We can say that we have some spectral data. This is our spectral data. And the problem is from the set of domains, we have to find the domain on the boundary of which the S functions of our problem is equal to the given functions. If it is clear, I'll go on. I have some problem. If I have in fixed domain, I have some problem. I have S functions of this problem, definitions of functions of this problem, and I have some given functions, G, X. I search a domain on the boundary of which S functions of my problem are equal to the given functions. This is inverse spectral problem with respect to domain. Formulating this problem, I solved the first one I spoke about. The first one is what to give to define the domain. I give the set of S functions of the considered problem and formulate problem by the given set of the S functions of the problem. I have to restore, to come back, find the domain of the considered problem. Here, S are S functions of the problem and the G are given functions. I want to say that this is the first, I can say, first formulation of the inverse spectral problem with respect to domain. What we'll use here, using our approach, we could prove some new formula for the eigenvalues of the Schrödinger equation. But I want to remember that Q here satisfies some additional conditions. We proved that eigenvalues of the Schrödinger equation may be calculated by this formula. Why we have max here? Because if eigenvalue is not simple, is multiple, then we put maximum and take maximum over all eigenfunctions corresponding to the this eigenvalue. This eigenvalue is simple, then we can take off this maximum. As you can see from this formula, there is some effect here. As we can see from this formula, boundary values of the gradient of the eigenfunction uniquely determines the eigenvalue of the Schrödinger equation. Indeed, I haven't met this fact in classical literature also, that gradient of the eigenfunctions on the boundary can uniquely define eigenvalue. From this relation, considering the definition of the S function, we obtain the next formula. This is simple. We put all the definition of S function and get this formula. Now, let us consider some simple cases. For example, one-dimensional case. This is Sturm-Liouville operator with Q. The additional conditions I put on the Q in two-dimensional case here is that Q should be in the form C divided by X squared. In this case, its functions takes the form. We have two S functions in the, as the S function indeed is defined on the boundary of the domain. In this case, as a boundary, we have the points A and B, and in A and B, its functions are eigenfunctions divided by eigenvalue, and the second one also. Only in the points A and B. The basic relation here, you see, is the integral. In one-dimensional case, takes this form. As you see, if we take the starting point of the interval A 0, then all its functions will satisfy this formula. This is the effects of the definition in one-dimensional case. If we have inverse spectral problem in one-dimensional case, it means that we have to define the point A or B. In this case, we have this simple solution that B must be equal to divided by S function of this problem. Two-dimensional case is if the S functions are constant, then this constant is equal 1 divided by mes d, for example, another effect. So here we prove some lemma that if f is a continuous function defined on SB, then for any D1 and D2, the expression, the relation is valid. B is a ball, I want to mention. Now, how we solve the inverse spectral problem with respect to the domain using all this one? We take CSB, the space of continuous in SB functions. We take some basis phi k. We extend this basis, but extend positively, homogeneously, continuously, and it is known fact that such function may be presented as a limit of difference of two positively homogeneous convex functions sequence indeed. This is known fact. You see here in the difference, we denoted by G and H. They are good functions, positively homogeneous convex functions. It means that they play the role of support functions for some domains. And if G and H are the basis, then the domains corresponding to these functions, we call them basic domains. It means that G is a support functions for G, domain G, and H is a support functions for the domain H. And we can substitute it to our formula, we get this one. Now, for the sake of simplicity, we will take only differences, not difference of sequences, only as a differences, where our G and H are closed bounded convex domain. Then we can represent our P using these domains. Now the problem is how can we calculate the coefficients alpha. Here are some operations related with working with convex domains. Here you cannot freely change the signs and the places. So we have to follow some strict, strong rules, and that's why we write in the form. And after some transformations, we arrive at this equation or system of equation, we can say, or in the simple form, we get the infinite system of algebraic indeed equation with respect to alpha k and alpha m. Solving this, now I'll give some algorithm. Now, what we have to do to restore our domain? We have some infinite system of algebraic equation with respect to alpha k and alpha m. We solve this problem. How to solve this is another question. And find coefficients alpha k. In step 2, we put alpha k in the representation P or by the basic phi, and find the function P. This is support function of sought domain. Then we calculate the subdifferential of the function P at the point 0, get some domain. But here there is some correctness problems. There is some correctness because solving inverse problems usually meet this problem. This equation can have some not unique solution. In this case, we have to check the convexity connection and choose the domain among all convex domains, considering the convexity condition. By this way, indeed, this is some, I want to say, analytic approach to solve inverse problem relatively domain. But we stopped here in solution in step with the infinite system of algebraic equation. Of course, here we can apply some numerical methods. It depends on the exactness rate, which part of the infinite system to take, and what kind of exactness condition should be satisfied. So this is only some approach to solution of inverse problem with respect to domain. And this is some approach how to generally formulate inverse problem relatively domain. Here is some idea how can we go ahead. How can we develop this? Regarding the development, I want to say that after some years ago, our publication, our results in some different journals regarding the our shape derivative formula and the application of our shape derivative formula to some spectral problems, to some shape optimization problems. I met probably about 5 papers in very good European journals devoted to improving our results and how this formula can be extended to the class of more general class of domains. Here we can see that strongly bound the set of bounded convex domains, but there are papers. One of them was published in Journal of Convex Analysis, I think published in France, and some French professors extended our shape derivative formula for a bit large class of domains. But generally, how can we go? It is known that, as you see the picture, each non-convex domain can be presented as a difference of 2 convex domains. Mathematically, it means that each non-convex function can be presented as a limit of differences of 2 good functions, or good sequence of good functions. It is proved that each non-convex function can be represented as a difference of good functions. But how? The problem is how. If we have some constructive method allowing us to represent each bad domain as a difference of 2 good domains, or each non-convex function as a difference of 2 good functions, then we can extend all the results obtained by introducing new shape derivative formula to the set of non-convex domains. Just now, it is proved that may be presented, but how it can be done, I don't know. That's why we cannot extend our results for non-convex domains just now. This is some, I can say, open problem. Here are some references, our papers and papers of our professors devoted to this topic. This is the end of my speech, dear Professor Allakhveran Ashuraliyev. I told you about formulation of the inverse spectral problem with respect to domain, and I offered some analytical numerical approach. How can this problem be solved? Thank you very much for your attention.